Hello everyone. In this section, we will be using the chi-square distribution to set a hypothesis test of different scenario. For example, I want to test a system if the probability of certain outcomes are the same for this system. Like throwing a die, is the probability of phase 1, phase 2, phase 3 the same, 1/6? Or the homogeneity of several systems. Maybe I have 3-4 systems and I want to test, are they producing the same outcome with the same probability? Like I have machine that produce pipe. Do these machines produce pipe of certain width, either okay, meet the standard, or larger or smaller with the same probability? Or sometimes independence. I have 2-3 variables. I want to see, are they independent or dependent on each other? So we use the chi-square test because in all these scenarios, we will always square the variable and normalize it. So now we will have a standard normal variable, which is described best by a chi-square distribution. So let's start with this scenario. In a casino, they use the die. So now you are questioning, is the die fair or does it show the phase 6 more often than other phases? Or maybe it shows the even phases more than the odd phases. So you set a null hypothesis. You say the probability of 1, the same as the probability of 2, 3, 4, all the way as the probability of 6, and these should be 1/6 if it's fair. So that's your null hypothesis. Now you conduct the experiment, throwing the die maybe 600 times and observe the value. Keep counting how many times the 1 appear, how many times the 2 appear, and the 6. And if the probability came 1/6, then it is fair die. If the probabilities change, then it is not. So let's look at this scenario. So for the die, there are 6 possible categories. I throw it 600 times. I observed phase 1 appeared 115 times. Phase 2 appeared 97 times. All the way to phase 6 appeared 86 times. Now, if the die is fair, I expect 1 appear 100 times, 2 appear 100 times, and so forth until 6 appear 100 times. That's what I expected if it's fair. But we know if we conduct the experiment, even if the die is fair, you will not get this, but you will get close numbers. So now how close is close to make a judgment that the die is fair? And how much deviation we should expect, and that's normal because when you conduct experiment, it won't always come exactly the same. Now that's the question. So one way to decide if the die is fair or not, I sum the differences between these. The smaller the differences mean the die is fair. The larger the differences mean the die is not fair. So I'm going to say, okay, I will sum the difference for phase 1, phase 2, phase 3. So this is observed 1 minus expected 1, or I. I stand for 1, 2, 3, 4, 5, 6. So I will do the summation here. I equal 1 to 6. So 115 minus 100 is 15. 97 minus 100 is minus 3. Now we have a problem. So if I sum these, there are some of them positive, some of them negative. I may end up 0, which tell me basically the observed exactly like the expected, but that's not the case. I may have here 150 and here only 50. Then here I will have positive 50 and here negative 50. And when I add them, I get 0. Then we're going to say, okay, we can solve this problem. It's easy. So we don't need negative. I will square it. So all the differences will be now positive. That's fine. But now, if I conduct the experiment 600 times versus 6,000 times, if the difference here for 600 times came 20, now if I conduct it for 6,000 times, it may come 200, the difference, because there are too many of them, even though it's the same die. To solve this problem, we normalize it. We divide by the expected value, EI. So if I conduct the experiment 600 times, EI will be 100. If I conduct the experiment 6,000 times, EI will be 1,000, and that will normalize it. Now, EI is a fixed number. The only variable here is the observed value, and it is squared. So this will follow a chi-square distribution with a degree of freedom. If we have 6 category or 6 summation here, 6 summation, 6 random variable I am summing, O1, O2, O3, then the degree of freedom n minus 1 or the category minus 1. There are 6 category, so that would be 6 minus 1. So these will follow a chi-square distribution with degree of freedom 5 for this example. And this is the test statistic. Now the smaller this value, I will conclude the die is fair. The larger this value, that provides strong evidence that the observed value are different than the expected value, so the null hypothesis is not true. That means the probability of phase 1 does not equal the probability of phase 2, 3, 4, 5, 6, and does not equal 1 over 6 if this is large. So now when we plot the chi-square distribution, it looks something like this, and this is xi squared. So if this value become large, then there is a strong evidence to reject the null hypothesis. That means it will be somewhere here, and they calculate this alpha, and that will be my p-value. The larger the test statistic, the smaller this alpha, less than 5%, that provide a strong evidence to reject the null hypothesis, which is H0, P1 equal P2 equal P6 equal 1 over 6. So let's solve this problem here and calculate xi and calculate the p-value and see for this experiment if the die is fair or not. So this will be here, and if I calculate x5 squared, it will be observed value is 115 minus 100 squared divided by the expected value 100 plus 97 minus 100 squared divided by the expected value 100 plus all the way to the last one, which is 86 minus 100 squared divided by 100. And if I calculate these, I will get 6.12. If I go to the chi-square distribution and look for here 6.12 for a degree of freedom 5. Let's see, that will be degree of freedom 5. The closest to 6.12 is somewhere between here and here. So our 6.12 is here. 9.23 is, that's what's in the table, 9.23. This alpha is already 0.1. So for somewhere between is here, it will be even more than 0.1. So alpha is larger than 10%. And if the p-value is larger than 0.1, there is no strong evidence to reject the null hypothesis. So there is a possibility the die is fair. So I cannot reject the null hypothesis. 6.12 is not a big difference. That could be the difference because of experiment variation. Now imagine if x squared came, instead of 6.1, came 12.88. Now alpha will be 0.25. So that is 2.5%. That's less than 5%. So there is a strong evidence to reject the null hypothesis. Okay, so that's one application of the chi-square test to set a hypothesis test to check the probability of a multinomial trial if it meets the specification. In this case, they are all equal and equal 1 over 6. I may have a different application of different probability. Then I will calculate the expected value based on the probability given and compare it to the observed value. Now, a second application for the chi-square test is to test the homogeneity of a system or of machines. So just imagine that you have 4 machines in the factory that produce pipes or pins. And the pins could be too thin or okay, meet the specification, or too thick. So there are 3 possibilities for the pin. And you want to test, are these machines, are they homogeneous? Are they uniform? They produce too thin with the same probability okay with the same probability, too thick with the same probability. That's what you need to test. So in this case, our null hypothesis will be the probability of the outcomes are the same for each experiment. If I think of these are experiment 1, experiment 2, experiment 3, experiment 4, then the probability of too thin for experiment 1 is the same as the probability too thin for experiment 2 and 3 and 4. And the probability of okay for experiment 1 and 2 and 3 and 4 are the same. And mathematically, we say this one. For each column, J, this is the column here, J, the probabilities are the same. 1 here stands for system 1. So 1 here stands for system 1, which is in this case machine 1. 2 here stands for machine 2. 3 stands for machine 3. And 4 stands for machine 4. Now J here could be too thin, or it could be okay, or it could be 3. So J I can assign too thin 1. When J is 2, that is okay. When J is 3, if J is 3, then that's too thick. So this J and here I. And this basically is the probability too thin for machine 1 is equal for machine 2, for machine 3, for machine 4. The probability okay for machine 1 is the same as the machine 2, 3, 4, and so forth. So how do we test these hypotheses? That's the question. How do we conduct the hypothesis test for the homogeneity of these machines? We have to construct the expected value and compare the observed value with the expected value. I have to find the probability of too thin, and it should be the same for machine 1 and 2 and 3 and 4, according to the null hypothesis. So if I want to calculate the probability of too thin, and it should be the same for all machines, then how many too thin do I have out of 500? See, these 500 basically machine 1 produced 120 pin. Out of this 120, 10 are too thin, 102 okay, 8 too thick. For machine 4, it produces 80 pin. Out of this 80, 10 are too thin, 60 okay, 10 too thick. So the total of pin produced by all machines are 500. Out of these 500, 66 are too thin. So the probability of too thin, then it will be 66 out of 500. And this will come 0.132 or 13.2%. And this, if the null hypothesis is true, that probability should be the same for all machines. And the probability, okay, will be the total for O2 out of 500, and this should be 0.804, and that's equivalent to 80.4%. And probability too thick equal, there are 32 out of 500. So this should come 0.064 or equivalent to 6.4%. And if you add all these percentages, you should get 100%. Okay. So if they are homogeneous, all of them the same machine, that the probability for each machine should be the same. And now I can calculate the expected value. So the expected value should be the following. Machine 1, how many too thin it has to make? Well, it produces a total of 120, which is the same as here. So then for machine 1, too thin for machine 1 should be, it produces 120 times the probability of thin is 0.132. This should give us 15.84, which is this. Okay, how many okay it produce for machine 1 is it produce 120 pipe. The probability of okay is 0.804, and this will come 96.48, which is this one. And here it was 15.84. And we can do all these for all machine. For example, for machine 4, how do we get these? Too thick for machine 4. Well, machine 4 produced 80 pipe, so that's 80 pipe. And if they are all the same, then probability of too thick is 0.064. And if you multiply these, you get 5.12, which is this. And that's how we construct the expected value. Our null hypothesis, all probability in the J columns, which are this one. This is J equal 1. This is J equal 2. This is J equal 3. This is the J, the columns, all equal. Then we construct our expected value if the null hypothesis correct. After we do this one, now we have to find the difference between the observed value and the expected value. If the difference is small, then yes, our hypothesis is true and the machines are all uniform. Homogeneity is true for all machines. And again, the same as before, we cannot just subtract and add because some difference will be positive, some difference will be negative, so we square them. And then we normalize them by dividing by the expected value. And here, why we have two summation, I here stand for the row. So we have 4 machines, 4 rows. So this I, capital I, equal 4. J here stand, you can call it category. Too thin, okay, too thick. So there are 3 of them. So J here equal 3. So for example, let's say I is 1, J is 2. Then this summation, if I is 1 of the summation, and J is 2, then this will be O, I is 1, J is 2, minus expected value 1, 2 squared divided by expected value 1, 2. 1 is the first row, 2 is the second column, so that is the observed value. Expected value 1, 2, I go to the table, expected value, this is 1 for row, 2 for column, that's the expected value. So I take the difference between these two, I square it, and divide by the expected value, which is this. And that's what this one. So you will be doing it for all these elements. So here the summation, these two summation, you're going to be doing, I have 4 times 3, 12. 12 subtraction and then squaring them. So basically you can visualize this summation here. I find the difference between this one and this one, square it, then divide by this. Then I find the difference between this one and this one, square it, then divide by this. And the difference between this one and this one, square it, then divide by this. And the same thing here, the difference between this one and this one, you square it, then you divide by this. And you're going to be doing it 12 times to get this value, the chi-square. Again, why it follow chi-square distribution? Because E are expected, so that's fixed value. The only variable here is O. And you square it, and you standardize it, so that's a standard normal distribution, and it will follow a chi-square distribution. The smaller x square, that means there is a strong evidence that they are homogeneity. The probability are the same for all of them because the difference is small. The larger here, xi square, then this alpha here will be smaller. That means the machines cannot be homogeneous, cannot be uniform. So there is a strong evidence to reject the null hypothesis. And that's the whole idea. So if we do this example, then this summation, I will just do a couple of them. X squared equal this with this one. So that will be 10 minus 15.84 squared over 15.84. Plus the next one, this and this. 102 minus 96.48 squared divided by the expected value, 96.48. So I am extracting this summation. Plus this and this divided by 7.68 plus all the way to the last one, this one and this one. 10 minus 5.12 squared divided by the expected value. If you do all the summation, you will get this value, 15.58. Now, when you look at the chi-square distribution, what degree of freedom you're going to be using? Well, the degree of freedom here is the number of system or row minus 1 times the number of column or category minus 1. So that would be 3 times 2 is 6. So the degree of freedom, 6 and square, and I am looking for 15.58, and I want to see what is this alpha. Is 15.58 large enough to conclude the machine cannot operate the same way? Some machine bring too thin pin more than the too thick. Other machine maybe bringing more okay than the remaining. So we go to the alpha and we look for a chi-square degree of freedom 6, and it's equal 15.58. So that's a degree of freedom 6 and 15.58, somewhere between these two. So alpha will be between these two values. So it will be less than 0.025 and larger than 0.01. For our test, it's enough that alpha is less than 0.025. So that is alpha less than 2.5%. So there is a strong evidence to reject the null hypothesis. So alpha is less than 2.5%. It's probably 2% or 1.8%. So there is a strong evidence to reject the null hypothesis, because the differences between the expected value and the observed value is just too large to justify that this probability gonna be the same for machine 1, 2, 3, 4, and this probability the same, okay, for machine 1, 2, 3. It seems like machine 2 produce maybe more okay than the too thin and the too thick. And if we really want just to see why they are not uniform, let's look at the probability of too thin for machine 1. It is 10 divided by 120. And this is 8.3%. So that's already far from 13.2%. For machine 2, that will be 34 divided by 200. So this will be 17%. And for machine 3, it will be 12%. And for machine 4, 12.5%. So they are varying from the 13.2 that we assume all of them will have 13.2%. So there is a big deviation. This comes close to the 13.2. This comes close, but this is much more. This is much smaller. So when we did the whole test, not just for one, we did it for okay and too thicks, and it came, the difference is just too large for them to be homogeneity. And the evidence is too strong to reject it. Okay, we can also use the chi-square test for independence between two variables. In this example, a manufacturer that produces steel pins, and there are two variables, length, it could be too short, okay, or too long, and the diameter. So this is the steel pin. One is length and one is the diameter. And the diameter could be too thin, okay, or too thick. So a machine produces these pipes or steel pins. And we want to know, is there a relationship between length and diameter? That means if the machine make the length too short, does it make the diameter too thick? Or if the machine make it too long, does it make the diameter too thin? Or are they independent? If the length came too short, the pin could be too thin with the same probability as okay as too thick. That's what we are trying to test. So the null hypothesis, the pin's diameter specification do not depend on the length specification. Basically, the column's probability the same. So the probability here of too thin, the same as the probability of diameter okay, or the probability diameter too thick for all these lengths. Same steps as we did in the previous example, except there we were testing the homogeneity between machine 1, machine 2, machine 3, machine 4. Here we are testing the independence between the variable length and the variable diameter. We need first to find the expected specification of the steel pins. So we have to calculate this probability, the column probability. That is the probability diameter tooth thin. So that will be the total, the machine produce 80 steel pin that have tooth thin diameter. Out of a total pin, it produce 1021. And if you calculate this, you get 0.0784, which is 7.84%. Probability diameter, okay, is 849 divided by 1021, you get 0.8315. So that is 83.15. Probability diameter too thick equal 92 divided by 1021. And this should give you 0.0901, which is the same as 9.01%. Okay, now if the null hypothesis of all these probability of too thin, the same for a pipe of length too short and a pipe of length okay, or a pipe of length too long. So how do I calculate the expected value here? Well, steel pin that are too short, there are 134 of them. So how many of these 134 too short are also too thin? It will be 134 times the probability of diameter too thin, 0.0784, and if you multiply these, you should get 10.5056. So round it to 10.5, which is this one here. If I want to calculate this number, if the steel pin length is too long, then there are 81 steel pin that are too long. If I multiply it by the probability of diameter okay, which is 0.8315, then I get 67.35, which is this one. Some rounding here. And that's how we calculate the expected values. Now we find the difference between the observed value and the expected value. And if the difference is very large, then our null hypothesis cannot be true. There is dependency between the variable length and the variable diameter. If the difference is very, very small, then the null hypothesis is true, which is the pin diameter specification do not depend on the length specification. Because when we calculated this expected value, we calculated based on the assumption of the null hypothesis that the probabilities of too thin, diameter okay, or diameter too thick are the same for all pipe that has length too short or okay or too long. That's how we got the expected value, based on this null hypothesis. So if we go ahead, same as before, x squared, and now the degree of freedom, we have 3 category for length, so 3 minus 1 is 2, and 3 category for diameter, 3 minus 1 is 2, so 2 times 2 is 4. So the degree of freedom is 4. And if I carry out the summation, you subtract the whole matrix here from the matrix here, and you square it, and you divide by the expected value. I'm gonna do it just for the few of them, just to give you idea. So that is observed value 13 minus expected value 10.5. You square it, divide by the expected value 10.5, plus the next one, observed value 117, expected value 111.43. You square it, you divide by the expected value 11.43, plus all the way for these until here, which is observed value 8 minus expected value 7.3. You square it, you divide by the expected value 7.3, and if you calculate this x squared, you should get 7.46. And if I look into the table for a chi-square of degree of freedom 4, that is equal 7.46, then alpha here will be, let's see, degree of freedom 4, and x is 7.46, so we move here. This is the closest to it, and this is 0.1. 7.46 even going to be here. So it's even larger than 0.1 because it's going to be somewhere here. So we go back to our example. P-value is larger than 0.1. So larger than 5%, the category. So there is no strong evidence to reject the null hypothesis. So there is a possibility that there is relationship between the length and the diameter. So this is p-value is larger than 10%. So there is no strong evidence to reject the null hypothesis. So there is a possibility there is a relationship between the length and the diameter. This should be here or not related. Okay. The next topic will be tests for variance of normal population using the chi-square. Are the variance the same, different, and so forth? Thank you.